Okay. Now photochemistry in detailed discussion for radiative and non-radiative transitions. Fluorescence, phosphorescence and resonance fluorescence. Now, before the lectures, we describe about radiative and non-radiative transitions, what are radiative, what are non-radiative. But now we elaborately describe all of the terms. Okay. Various mode of radiative and non-radiative decay. Non-radiative decay, that should be this transition involve the return of the activated molecule from the higher excited state, that should be S3, S2 or T3, T2, they are higher excited state, to fast excited state, that should be S1 to T1. They are termed as non-radiative decay. These transitions do not involve the emission of any radiation, are thus referred to as non-radiative or radiation-less transition, as when the transition can be take place, but due to transition there should be no radiation emit or absorb. Okay, so that should be termed as non-radiative or radiation-less transition. In before the lecture we described there should be transition can be there from S1 to S0 also and T1 to S0 also. Okay, but there should be not given, but that is also right, that is S1 to S0 can be internal crossing can be there, internal combustion can be seen, and T1 to S0 can be inter-system crossing can be seen. Okay. But due to this internal combustion and inter-system crossing, no radiation that should be emitted. So that's why these transitions are termed as non-radiative transition. Okay. So our common sense tells us that when any molecule get excited by absorbing some amount of energy from ground state, and then they undergo transition ground state to excited state. Okay, they have sufficient amount of energy. Okay, so when they go back to the ground state, they should emit some amount of energy. But in that case, ISC and IC, there should be no radiation can be re-emitted or no radiation that should be re-emitted in case of non-radiative transitions or IC and ISC processes. Okay. The energy, now the question is the energy go in the energy lost can be take place. Okay, so how the energy that should be lost? The energy of the activity molecule that should be dissipated in the form of heat through the molecular collision, as there should be some collision can be occurred. So due to this collision the energy can be dissipated. So so from excited state to ground state transition, no radiation can be seen. That's why IC internal combustion and ISC inter-system crossing are termed as non-radiative decay. Okay. The molecule may also lose energy by another process that should be called inter-system crossing, ISC. Now we termed as IC, internal combustion, that should be occurs is less than about 10 to the power minus 11 second. That should be less than about 10 to the power minus 11 second. Now we consider ISC, inter-system crossing. This process involves transition between states of defined spin, that is defined multiplicity, as per example S2 to T2, S1 to T1, and there should be spin that should be changed. Okay. So these transitions are also non-radiative or radiation-less. Actually, spectroscopically, ISC is a forbidden process. So their rate that should be slower. So by this case, we can see that this rate of IC is much slower than IC. Okay, as ISC is a symmetry forbidden process, as singlet excited state and triplet excited state, transition are forbidden process, as their spin change and their spin multiplicity that should be changed. Okay. Now we consider radiative transition. We can see in previous slides this. Okay, there should be, you see, singlet excited state. Okay, this is excited, this is excited. So there should be total spin 0 and there should be total spin 1. So spin change, overall spin change, and there should be spin multiplicity 1, there should be spin multiplicity 3. So that is must be 1 to 3 or 3 to 1 spin multiplicity that should be changed. Okay. Okay. Now we consider radiative transition. Radiative transitions are basically two types. One is fluorescence, other is phosphorescence. There should be excited state to ground state transition, some amount of energy radiation, some amount of radiation that should be re-emitted. That's why fluorescence and phosphorescence termed as radiative transition. We can see here there should be from S1 to S0 we get fluorescence, and T1 to S0 we get phosphorescence. Okay, they are basically termed as radiative transition. That's why this absorption, fluorescence and phosphorescence termed as straight line. Okay, and all rest that should be all that should be curved line. That should be curved line. That should be curved line. Okay, that is also curved line. Curved line. Okay, curved line means non-radiative and straight line means radiative. Remind it, curved line that should be non-radiative, straight line that should be radiative. Okay. Now fluorescence, when the molecules are exposed to UV or visible light of the appropriate frequency, it will be absorbed in a femtosecond. Okay, 10 to the power minus 15 second. When the molecules are exposed to UV or visible light of appropriate frequency, it will be absorbed in femtosecond, means 10 to the power minus 15 second, means femtosecond. The molecule moves from the ground excited state to the first excited singlet state, and since the average lifetime of the excited singlet state that should be very small, excited singlet state that should be lifetime is very small, 10 to the power minus 9 to 10 to the power minus 6 second. A direction transition from the excited singlet state back to the singlet ground state may take place with the emission of photons and radiation rays with a shorter time. Okay. Then phosphorescence, and these kind of emissions of radiations is termed as fluorescence. So there should be always remember, for transition in fluorescence, time will be shorter or rate will be faster for fluorescence than phosphorescence. Phosphorescence is a slower process due to two reasons. One is symmetry forbidden, other is triplet excited state are long lived. That's why. The mechanism is molecule S0, H no absorption can be there. So molecule go S0 to S1, then again radiative emission. So they again go S0 and H nu. Now we consider, in previous lecture there should be some confusion, right, about the lifetime of excited singlet state and excited triplet state. So always remember, 1 by 10 to the power 9 that should be smaller than 1 by 10 to the power 5, right? 1 by 10 to the power 9 that should be smaller than 1 by 10 to the power 5. How can we conclude? Always remember, 10 to the power 9 is greater than 10 to the power 5. 1 by 10 to the power 9 and 1 by 10 to the power 5, when both side of the greater than or less than, that should make inversed. When the both side of the greater than or less than, both side of the number of greater than or less than, that should be get inverse. There the sign that should be changed, and so the sign can convert it to this. Okay, so we get 1 by 10 to the power 9, that should be less than 1 by 10 to the power 5. So we can conclude this: 10 to the power minus 9 is less than 10 to the power minus 5. Okay, so by this way we can say that is lifetime of excited single state. Excited single state is low. This value is low value, and this value is low value. Okay, and this value is high value. Okay, so by this way we can say that is singlet excited state are short lived and triplet excited state are longer lived than singlet excited state. Okay, now we consider today's slide. Now we consider phosphorescence. This is the another possibility of the radiative transition. That is, after that absorption of light of a suitable wavelength, the molecules raised to excited singlet state. Okay, lifetime 10 to the power minus 9 to 10 to the power minus 6 second. It may undergo transition to a metastable triple bond because triplet excited state are not stable enough. That should be actually stable, but they are actually metastable. We can say they are actually metastable. So metastable triple point, lifetime 10 to the power minus 5 to 10 to the power minus 3 second. Longer lived, 10 to the power minus 5 to 10 to the power minus 3 second. And sometimes thereafter returns back to the stable singlet ground state by emission of an ultraviolet or visible radiation of photons. Okay, when triplet state to down singlet state transition can be occurred, there also some radiation can be re-emitted, and this type of transition are termed as phosphorescence. Okay, the process of crossing from excited singlet state to a metastable triplet state is called as ISC, intersystem crossing. That is S1 to T1. That should be termed as ISC, intersystem crossing. Okay, it does not involve any emission of photons, hence non-radiative transition, and the mechanism of phosphorescence, that should be molecule first one in ground state, that should be designated as S0. Then after H nu absorption, S0, the molecule will go S0 to S1. Then there should be one process ISC, that should be go T1, and then again this. Okay, this is not correct. This should be correct. Okay, so S0 to S1, then S1 to ISC T1, and T1 to again S0 to H nu. We also see in that case, that is lifetime 9 to 10 to the power minus 5 second singlet excited state, and triplet excited state, that should be 10 to the power minus 5 to 10 to the power minus 3. They are also given singlet excited state is less stable and shorter lived. It's very important. Okay, shorter lived. And that is triplet excited state is a longer lived. That's why fluorescence rate of fluorescence, that should be higher than rate of phosphorescence. Okay, rate of fluorescence, that should be higher than rate of phosphorescence. Phosphorescence is a slow process. Okay, now we consider there should be, that is pi to pi star, sigma to sigma star, but always remember in electronic energy there should be some shift can be there. Normally if double bond is present, there should be pi to pi star, and if lone pair is present, there should be n to pi star. Okay, but when the solvent is polar, there should be some shift can be there. When the molecule go longer wavelength, that should be called bathochromic shift. Bathochromic shift. Okay. When go shorter wavelength, that should be termed as hypsochromic shift. Hypsochromic shift. Okay. When lambda wavelength go longer region, that should be bathochromic shift, and when go shorter wavelength, that should be termed as hypsochromic shift. So when ethylene attached with conjugated double bond, there should be lambda increases, longer wavelength, visible range, so bathochromic shift occur. Okay, as when we observe the big beard, that is the 7 colors of visible range, there should be the longest wavelength is red and shortest wavelength we can say blue. So we can say bathochromic shift as a red shift and hypsochromic shift as a blue shift. Okay. Okay. Now consider when intensity when intensity increase, that should be called hyperchromic shift. When decreased, that should be called hypochromic. Okay, CHROMIC, hypochromic shift. Okay. Now when polar solvent are taken, on that case, that is pi star more stabilized than pi. Okay, N that should be more stabilized than pi star. Yeah, that should be pi. Okay, so stability order in polar media, that is pi star, that should be more stable, then N, then pi. Okay, so that's why when polar solvent that should be taken, on that case pi to pi star is easier. So on that case pi to pi star go hypsochromic shift. Okay, blue shift. And that is always remember, okay, there is not right, N is more stable as it is non-bonding. Non-bonding is more stable in polar media, as this is can engage in hydrogen bonding. So that's why N to pi star transition is not favorable in polar media. So that's why when solvent taken as polar solvent, there should be Ns to pi star, pi s, energy have to be used more. Okay, so there should be always remember what is given in this solvent. There should be solvent considered as a polar solvent. Okay, that is should be polar. Okay, so this is our less polar, this should be our more polar. Okay, and in polar medium there should be stable more N, then pi star, then pi. So pi to pi star, that should be easy, and N to pi star, that should become difficult. So that's why in that case, in S spot solvent means polar solvent. Okay, S spot solvent means polar solvent. For polar solvent, pi to pi star, that should be energy is less than the normal pi to pi star. Okay, and in polar medium, there should be, that is non-bonding to pi star, more energy have to be needed than normal N to pi star, as non-bonding is more stabilized than pi star. Okay. Okay. As for example, we can say in non-polar medium, that is hexane, and that is polar medium water. Okay, so by this concept we can say that is in hexane medium there must be N to pi star and pi to pi star, both suppose possible. So when water is taken as a polar solvent, there should be lone pair is more stabilized, then pi star, then pi. So as lone pair is more stabilized, so lone pair that is non-bonding to pi star is not favorable, as non-bonding is more stabilized. So when system go unstable state, that should be not favorable. So non-bonding to pi star are not favorable, so more energy have to be provided. So energy that should be more needed. Similar analogy, when pi to pi star is more stabilized in polar medium, so pi to pi star can be possible, as pi is unstable respect to pi star and pi star is more stable than pi, so easily pi to pi star can be there. So that's why pi to pi star transition less energy have to be provided for polar medium. That should be applicable for electronic spectra. Now we consider PBSC-Jablonski diagram. There should be amount of absorption, that should be radiative. There should be internal conversion from same excited state, that is singlet to singlet and triplet to triplet excited state. And there should be internal conversions are non-radiative transitions, that's why that's curved line. And there should be, can be observed deactivation. Before product formation, we first there may be deactivation can be there. There should be deactivation can be there. Excited singlet state to lower excited state. Okay, deactivation. And there also fluorescence can be there. Okay. Okay. Now application. Basically application of fluorescence, I think. Fluorescence, application of fluorescence, that should be determination of vitamin B1 and B2. B1 is thiamine, B2 is riboflavin. Okay. Vitamin B12, cyanocobalamin. Okay. Vitamin H, biotin. Okay, so on. Now we go, vitamin B1 is thiamine, vitamin B2 riboflavin. Thiamine is a non-fluorescent various oxidation product. Okay, that is thiochrome fluorescences with blue color. Okay, so thiamine is a non-fluorescent various oxidation product. Actually, thiamine is a non-fluorescent compound. Okay, but when it oxidized, its oxidation product, you can say its oxidation product, that should be thiochrome, that should be fluorescences with blue color. Okay, now riboflavin is a fluorescent material, but its oxidation product, that should be non-fluorescent. So useful for detection of B1, B2, we can use fluorescence concept. Okay, as that should be defined with respect to fluorescence. Thiamine is non-fluorescent, but its oxidation product, that should be thiochrome fluorescences with blue color. Okay, riboflavin, that should be B2, vitamin B2, that should be fluorescent material. Its oxidation product is non-fluorescent, so it's useful for detection of B1 and B2 vitamin. Next one, in medicine, when fluorescent liquid are injected to human or animal body, they injected in the internal organ will fluorescence. Okay, on that case, the internal organ, that should be fluorescence and can be observed fluorescent microscope. Okay, so the inner part can be that should be easily seen. So what is the problem of the patient can be easily detected. Okay, now there should be again absorption, internal conversion, ISC, that is singlet excited state to triplet excited state, IC intersystem crossing, that should be non-radiative curved line, and there should be T1 to the singlet excited state collisional deactivation can be there, as well as phosphorescence can be there. Phosphorescence is a radiative, so straight line. Okay, okay. So there should be application of phosphorescence also. That should be determination of aspirin. Aspirin means what? That should be acetyl salicylic acid. Acetyl salicylic acid in blood serum by phosphorimetry at liquid N2 pressure, N2 temperature. Liquid N2, and with phosphorimetry we can determine that is aspirin. Okay. Next one, determination of cocaine and atropine in urine. In urine, there is cocaine in urine, are any cocaine or atropine that should be present, or if they present, how the amount of atropine or cocaine that should be present can be detected by phosphorescence. Okay. Next we termed as last topic, that should be resonance fluorescence. When an instant light that should be falls on a substance, okay, when an instant light falls on a substance, it emits light of same frequency. It emits light of same frequency as that of incident light. And this phenomena is known as resonance fluorescence. When the substance absorbs some amount of light, and that should be emit same frequency of light. On that case, this phenomena is termed as resonance fluorescence, and there is no vibrational cascade generally. Actually, when molecule get absorb some amount of energy, it activated and it go excited state. But when they go excited state, there should be some amount of energy loss due to due to vibrational cascade, due to some collision, due to some phosphorescence, due to some other phenomena. So there should be same amount of light cannot be emitted. But when molecule takes same amount of absorption, radiation by absorption, and same amount of radiation that should be emitted, on that case, that is in absorption of radiation equal to emission of radiation. On that case, this phenomena is termed as resonance fluorescence. Okay, there should be no loss of energy. Okay, in such cases, so what it is clear, that is resonance fluorescence. What is resonance fluorescence? There should be always remember, that is molecule absorbs some amount of energy and it re-emit exactly same amount of energy. Okay, on that case, this phenomena is termed as resonance fluorescence. Okay, in some cases, the absorbed energy is almost immediately emitted back within a time interval of about 10 to the power minus 8 seconds. That is in the meantime. In such cases, that is the absorbed energy that should be immediately emitted back. Okay, that is in the time interval 10 to the power minus 8 seconds. Resonance fluorescence is generally found with atoms absorbing light waves, that is X. Suppose X is the material who absorb H nu, that is energy, and get excited to produce X star. Okay, now X star re-emitted again energy and produce again X and H nu. Okay, so there should be this H nu and this H nu should be same. That's why we get resonance fluorescence. Okay, now for example, when Hg vapor, so again clear, that is X, that is the starting molecule, that should be absorb H nu and then again produce X star, that is excited. And now X star, that should be excited, that should be emit some radiation and produce X plus H nu. This is the H nu. This is the H nu that should be absorbed. This is the H nu that should be emitted. That should be equal. Then we can term as resonance fluorescence. Okay. Okay. Now the example is, when Hg vapor are exposed to UV light of wavelength 2537 angstrom, it excited from ground state H0 to state, that is P1C. When Hg vapor, mercury vapor, that should be exposed to UV light of wavelength 2537 angstrom, it is excited from ground state S0 to state P1C. That should be HgS01 ground state, that should be absorb H nu and go Hg star P1C. Hg star P1C, that should be excited state. Okay, so Hg ground state to convert into excited state by absorbing H nu. Now, if excited atom returns to ground state, it emit again same wavelength, that should be 2537 angstrom. Same wavelength, that should be 2537 angstrom. That should be 2537 angstrom. Again, this excited state, which that should be produced, emitted H nu and produce again the ground state only. So in previous case, 2537 angstrom wavelength absorption, HgS01 ground state convert into Hg star P1C. Okay, and by using same wavelength emission, 2537 angstrom wavelength radiation emission, excited state convert into ground state. Okay, so in first case this H nu and the second case this H nu, that should be equal. Okay, similar H2 which having no vibration cascade, that also show resonance fluorescence, because when vibration cascade can be there, when vibration cascade that should be there, there should be some energy lost. So on that case the absorption frequency not equal to emission frequency. Okay, so we cannot term as resonance fluorescence. But when vibration cascade is zero, vibration cascade is not seen, on that case energy loss is not possible. So on that case, that is absorption frequency or absorption wavelength or absorption energy equal to emission frequency or emission wavelength or emission energy. Okay, we can term it as resonance fluorescence. Okay. So what are the summary? Summary that should first we learn, that is non-radiative transition and radiative transition. Non-radiative transition, that should be when molecules get by absorbing some amount of energy get excited and go to excited singlet state or excited triplet state. But when they do not emit any type of radiation, this type of do not emit any type of transition, when they go back to the ground state, this type of radiation are termed as non-radiative transitions. Non-radiative transitions are basically two types. One is internal conversion IC, other is internal inter-system crossing IC. When singlet to singlet transfer can be there, are termed as internal conversion, singlet to singlet or triplet to triplet, and singlet to triplet or triplet to singlet conversion are there, that should be termed as IC, inter-system crossing. But for fluorescence and phosphorescence, there should be definite amount of energy that should be radiated. There should be radiation can be seen. So fluorescence and phosphorescence are termed as radiative transition. Okay. Now always remember, for fluorescence, that is, as we know, singlet excited state are short-lived, so the rate will be faster than phosphorescence. And phosphorescence, there should be triplet excited state are longer-lived. First one and second one, that should be symmetry forbidden process. As we know, singlet to triplet transition are symmetry forbidden process. So on that case, phosphorescence is lower and phosphorescence always keep lower intensity. Now, as we know, for polar solvent, there should be pi to pi star and non-bonding to pi star transition, that should be having some different variation. Because due to polar solvent, non-bonding is more stabilized than pi star and pi star is more stabilized than pi. So, pi to pi star transition is more favorable, so less energy used. But non-bonding is more stabilized than pi star, so non-bonding to pi star transition, that should be less favorable, so more energy have to be provided. Okay. This is same, that is IC, and there may be some deactivation can also be seen. Fluorescence application, that is we can determine vitamin B1 and B2. There should be vitamin B1, thiamine. Thiamine is non-fluorescent material, but it oxidation product, that should be fluorescences, and riboflavin, that should be fluorescent material, but it oxidation product, that should be non-fluorescent. We can detect by fluorescence concept. Okay, and also by using some fluorescent material injection in our inner organ can be visually can be seen, and we can detect the problem of the patient. Okay, there must be same analogy. And the application of phosphorescence, there should be deterioration of aspirin in blood serum by phosphorimetry at liquid nitrogen temperature, and determination of cocaine atropine, that should be present in urine. And last one topic, that is resonance fluorescence, that is when the molecule absorbs some amount of energy and they also exhibit radiation, emission radiation, same amount of energy. On that time, the phenomena is termed as resonance fluorescence. When the frequency of the absorption equal to frequency of the emission, that should be equal. On that case, we can say the phenomena is resonance fluorescence. Example is Hg vapor. Example is hydrogen. For hydrogen, where no vibrational cascade present, on that case resonance fluorescence can be occur, as when vibrational cascade is seen, on that case some energy should be lost, so there must be absorption frequency is not equal to emission frequency, so resonance fluorescence not to be seen. Okay. Okay, thank you so much.